Okay, good afternoon, everybody. This is question 73 from chapter 11. This question is asking for the use of this data over here. Like we've got temperature data and we have pressure data to determine both an enthalpy of vaporization. So let's put that up here. Empathy of enthalpy of vaporization, and the normal boiling point. So, normal boiling point. Remember, that's the boiling point when the pressure equals 1 atmosphere. So let's put that up there too, just so we don't forget that. Okay, so if you've got pressure and temperature figures, and you're looking for vaporization enthalpy here, the equation to use, the formula to use, is the Clausius-Clapeyron equation, which is a rather bulky integrated expression that looks like this here. Enthalpy. Blah, 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 blah. Oh, whoops. I guess that's not a discrete value. That's going to be a delta value. Vaporization enthalpy. That's going to be divided by the gas constant, and that is going to be multiplied by some 1 over like delta T, if there's such a thing. Okay, so that's sort of what this thing looks like. This is a linear expression, right? This can be written like this equals, and like where all of this stays the same. Then, and because this is a difference in logarithms, and this just becomes an addition over here, this ln p1 here. So this is something that is going to give you a straight line. And when you think about it in terms of that, actually, let's just write that out quickly. Let's write the whole thing out, because when we look at it like that, then we can sort of see what our options are for solving this thing. And you can really go 2 routes. You can stick all this data in Excel, and you can plot yourself something. It is gonna give you a linear relationship, and then you see if it's not obvious now, it's gonna be obvious in a second. We're gonna get the slope out of the the enthalpy value out of the slope. Okay, plus ln p1. There we go. That's our full expression. So this is your y, this is your m, this whole thing here is your x, right? And this is your b. So equals mx plus b. Okay, so yeah, so same sort of idea. You can plot this data like this. You'll be plotting ln of p over here, and you'll be plotting 1 over t here, and you will get yourself several points that decrease like this, right? And you can get a straight line out of that. Your straight line out of this is going to be equal to this here, negative vaporization enthalpy over R. So I'll put that over here, over R. And this is gonna, I guess this would have the advantage also, if you're linearizing this thing, then you're gonna get the average, like the arithmetic mean, or the average of a couple different values, where it's gonna be like what you end up calculating is going to be sort of the sum of however many of those things you have in terms of data points. So this is still vaporization, like that, and that does help. That will give you a more precise answer, but you can also just plug in a couple of values out of the table, and you can calculate your way to it like that. I'm going to show you that way so that I don't have to back out and screen share into Excel, but just keep in mind you could absolutely go that route, and you will get a perfectly accurate answer. Okay, so I'm just going to go for a couple values here. I went for the second and the third one because I have some sort of I don't know, I just don't believe in first or last values for whatever reason. I got a stereotype against them. It's working for me, and I'm sticking to it. So no first, no last. Okay, so there's a couple pressure values. Notice that there's no units going in here. A reason for that is that it doesn't matter. These are going to be canceling each other out, and there's like logarithmic functions of units are not defined anyways. So we're going to be multiplying this by the gas constant. All right, so this is going to have some units. This is going to be joules per mole Kelvin. And then we're going to divide this entire thing by the x value here, right? Sorry, I guess I've skipped a couple steps here, but I've put this back together in this form, right? I've multiplied this by R, and now I'm dividing it by this 1 over T2 minus 1 over T1 to isolate the negative vaporization enthalpy. All right, so the only way that, and pay attention to the values you choose, but the only way that you could screw this up is to pick values that oh, whoops! I just realized I did pick the first one. What a guy. Anyway, so to pick the wrong temperature to go with the wrong pressure and such like that, that will get you into trouble. But otherwise, this is very straightforward plug and play stuff. These are both in Kelvin, so the Kelvin is going to cancel out from this here. And this, again, doesn't matter. We're left with an answer in joules per mole. We're just going to multiply this by -1 now, too. And that gives us 24722.8. Right. Joules per mole. And we'll put this straight into kilojoules to give us an easier number to work with. I did this with a couple sets, so if you plug this in your calculator, I wrote down the different numbers in my formula, but I think I actually calculated that value between these here, right? So if you run this in your calculator and you don't get my number here, try it with these two instead, because there's good reason that I avoid first and last numbers, so you may see exactly why. Okay, so that gave us our enthalpy of vaporization. So that's a check mark there. I guess we can put that up here. So that's 24.7 kilojoules per mole. Equals that. Now we're looking for the normal boiling point. I'm gonna have to erase some room for myself here. Erase. Okay, so the normal boiling point is also substitution, more plug and play. We're just going to put the pressure equaling 1 atmosphere in for one of the pressure values in that expression, and then we're just going to solve for the temperature that goes along with it. So let me just pull up my pre-done calculations here. So this is going to be, when this is solved for, well, I guess I could show that first, actually. Let's start from this one here. Vaporization. Do this a few times and you take a lot of it for granted, but you should always remember to run at the slower speeds. It helps you not miss things too. Definitely doesn't hurt. Okay, so we can keep this intact. We're looking for one of these values here. So if we do sort of the same idea, we're going to multiply this by R, right? And that's going to cancel out the R here. We're going to divide out by the enthalpy of vaporization, all right? And that will cancel out that term there. And then we're left with these ones here. So we'll just add 1 over T1 to both sides. I've run out of room here, but that's what we're going to do, and that will isolate us 1 over T2, right? And then we'll put the pressure equaling 1 atmosphere into P2, and then we're going to be off to the races here. Okay, so easier said than done, but here we go. So 1 over T2. So we're just gonna write this whole thing out with the conversions. We have the pressures in millibars. So I guess we'll just we'll put everything in bars. That'll be the easiest way to do this. So let's multiply that by 1.325 pascals per atmosphere. Oh, I just put kilopascals. Okay, well, never mind. We'll just keep going. We'll convert kilopascals instead of atmospheres. All right, so 1 bar over 100 kilopascals Okay, that's that one done. So remember again, this was P2. That's the 1 atmosphere, the normal boiling point that we're trying to solve for here. And we'll put that over 87.1. This is millibar, right? I'm just using value number 1 in this case. Because we're coming in with a different one, I'm not as leery against the 87.1. The stereotype doesn't hold in this case. And we're going to have 10 to the negative 3 bar per millibar here. Okay, so that is going to give us answers in bars both ways, which means we will cancel out all of our units from the logarithm term, right? Which is good news. It means we're good to go here. Okay, so let's multiply this by the 8.314 J over mol, right? Let's divide this whole thing by the enthalpy of vaporization. Do be careful in this case. I erased my other answer, but I did keep the numbers elsewhere. We need the enthalpy back in joules, right? So I ought to have written that off to the side. If we're dealing with this here in joules, then you've either got to divide this down or you've got to divide that up. So let's write our full number here. And this also has to be negative. Don't forget that either. 2, 4, what is this? 7, 2, 3.8. Hopefully that was the right. Hope that's the right value here. Okay, and this is joules per mole. All right, so that's gotten rid of that. We are left with something in 1 over K. Right, which is perfect. That's going to give us exactly what we want. And don't forget, we're adding to this 1 over T1. Right, so I went with 87.1 for the pressure, so that's going to have to be 1 over 200 Kelvin. I do apologize for the disastrous writing here, but yeah. It is what it is on this digital drawing pad. Okay, that's given us room enough up here to get, what did I get? 4.17 times 10 to the negative 3 Kelvin. Actually, that's negative 3 over Kelvin, actually, because of this 1 over K thing. So if we take the inverse of this, then we'll get our temperature, and we do find 239.6 Kelvin. So I didn't mention this earlier when I was calculating the enthalpy. I stopped at this value here because we only have 3 significant figures for the temperature. So we're going to do the same for the temperature that we just stopped at. So we're going to round that to 240 Kelvin. And there you go. That's the final answer. That gives us our normal boiling point, 240 Kelvin. And there you go. That's Clausius-Clapeyron equation.